Hello everyone. So in today's video, we are going to go over this paper, Text Detoxification Using Large Pre-trained Neural Networks by David Dale, Anton Voronov, Darina Dementrieva, Varvara Logasheva, Olga Kozlova, Nikita Semenov, and Alexander Pashiko. So I'm really sorry if I mispronounce any of those names. So as you can see, this paper is pretty recent. On this edition was dated 18 September 2021. Also, I haven't read this paper book before, so this would be my first time reading it with you guys. But the title seems quite uh, interesting because text detoxification is one of the areas of research which I'm really interested in. So the abstract, we present two novel unsupervised methods for eliminating toxicity in text. Our first method combines two recent ideas: guidance of the generation process with small style conditional language models and use of paraphrasing models to perform style transfer. Alright, so they are utilizing style transfer essentially. We use a well-performing paraphraser guided by style-trained language models to keep the text content and remove toxicity. Our second method uses BERT to replace toxic words with their non-offensive synonyms. We make the method more flexible by enabling BERT to replace mask tokens with a variable number of words. Alright, so it's not like if you have one word, it will be changed to another word only. It could be a bunch of words which come in place of that word. Finally, we present the first large-scale comparative study of style transfer models on the task of toxicity removal. We compare our models with a number of methods for style transfer. The models are evaluated in a reference-free way using a combination of unsupervised style transfer metrics. Both methods we suggest yield new SOTA results. So SOTA is basically state of the art. So basically they're using a style transfer problem approach. So they've modeled this as a style transfer problem. So if you're not familiar with style transfer, my past three videos have been on it, but I'll just give you a brief description. So each sentence, say S, has two attributes. It has some content and it has some style, right? So a style transfer problem is generally to take the sentence S and convert it into, say, some sentence S dash which has the same content but it has some new style, say ST dash. So essentially this is the problem. So suppose you have a positive review, you might want to convert it into a negative review or a negative review to a positive review. So now you might begin to see how this can be useful for text detoxification. So in one idea was to use language style transfer and paraphrasing models. So I haven't read the paper, so but judging by this, I would guess is uh, they they would take the toxic comment or the toxic piece of text, paraphrase it to get the crux of the text, and then use a style transfer model to reduce the toxicity. So maybe for them, toxicity is a style, and a non-toxic message is another style, and then they get this uh, detoxified message which they can output. So this is just me guessing by reading the abstract. Let's see how correct or incorrect I am. So introduction. Identification of toxicity in user texts is an active area of research. The task of automatic rewriting of offensive content attracted less attention, yet it may find various useful applications, such as making online world a better place by suggesting a user posting a more neutral version of an emotional comment. The existing works on text detoxification cast this task as style transfer. The style transfer task is generally understood as rewriting of text with the same content and with altering of one or several attributes which constitute the style, such as authorship, sentiment, or degree of politeness. So, suppose you have a text written by a person A, so it reflects the style of writing of person A, and suppose you want to convert it to person B, then uh, you need to effectively keep the content the same while incorporating the style of writing of person B and remove the style of writing of person A. So, despite the goal of preserving the content, in many cases, changing the style attributes changes the meaning of a sentence significantly. So, in fact, the goal of many style transfer models is to transform a sentence into a somewhat similar sentence of a different style on the same topic. So, it's obviously not possible. Uh, so, it would be very difficult to retain the content 100%, right? Because even as humans, we might face difficulty in converting text from one author to the other while preserving the content as it is, because even the content has some hints of style. So they want to keep it as close, but they also need to do the style transfer part. So we suggest that detoxification needs better preservation of the original meaning than many other style transfer tasks, such as sentiment transfer, so it should be performed differently. So this is because if you go back and see their initial plan, it was to suggest it to someone who might be posting it online. So suppose you totally detoxify it and someone was posting, say, some sort of absolute hate speech, and you give him a non-hate version, then of course he would just cast away the suggestion. But suppose you give him a neutral version or a less hateful version, then the person would obviously it might still go and ring a bell at the back of his mind. So we present two models for text detoxification which have extra control for content preservation. The first model, para-JD, is capable of fully regenerating the input. It is based on two ideas: external control of an output of a generation model by a class conditioned language model, and formulating of style transfer task as paraphrasing. Alright. Being based on a paraphraser model, para-JDI explicitly aims at preserving the meaning of the original sentence. Okay. The second approach, conned BERT, inspired by Wu et al., follows the pointwise editing step. It uses BERT to replace toxic spans found in the sentence with the non-toxic alternatives. The semantic similarity is maintained by showing the original text to BERT and re-ranking its hypotheses based on the similarity between the original words and their substitutes. Interestingly, BERT does not need any class condition pre-training to successfully change the text style from toxic to normal. Alright. So I guess these two models are pretty clear. One of them is using a paraphraser followed by sorry, a paraphraser followed by then a style transfer setting, while conditional BERT is looking for toxic spans, then finding the non-toxic alternatives. So in addition, we perform a large-scale evaluation of style transfer models on detoxification tasks, comparing our new model with baseline and state-of-the-art approaches. We release our code and data. So this is the code, I guess. I'll just keep I'll just have a copy with me. Sure. So we propose two novel detoxification methods based on pre-trained neural language models, para-JEDI. So paraphrasing, para stands for paraphrasing, and JEDI, and conditional BERT. Alright. What is this referencing to? This does seem a bit interesting. Despite the goal of preserving the content, right? So it changes the meaning. So if the sentence was, Gotham say that beard makes you look like a Viking, Gotta say that hair makes you look like a mermaid. So these are examples from male to female writing, but you can see that the meaning has totally changed. So we conduct an evaluation of these models under comparison with a number of state-of-the-art models for text detoxification and sentiment transfer, and release the detoxification dataset. We create an English parallel corpus for the detoxification task by retrieving toxic and safe sentence pairs from the para and empty dataset. We show that it can further improve our best performing models. So I guess they have their data here. Oh, so maybe towards the end I can download it and show it to you guys, or you can just go ahead and head out to this original GitHub repository and have a look at it. So related work. One of the most straightforward ways of solving style transfer task is to translate a source sentence into the target style using a supervised encoder-decoder model. Since the source and the target are in the same language, pre-trained language models such as GPT-2 can be applied for this task. Fine-tuning them on a relatively small parallel corpora gives a good result. However, this method is used quite rarely because of the lack of sufficiently large parallel data. The rest of the described models are trained in an unsupervised way. So basically what they're saying is it's difficult to find datasets where you have the same sentence where the content is retained and the style is changed. So you have to resort to unsupervised learning due to lack of such data. And the pretty straightforward method would have been to use an encoder decoder model, but due to lack of this parallel data, you cannot do that directly. Now we have pointwise editing models. A relatively easy yet efficient style transfer method is to leave the sentence intact and manipulate only individual words associated with the style. So delete, retrieve, generate framework by Lee et al. If you remember or if you've seen the last video, we saw a modification of this very uh, paper. So they have built on this paper and created new transformers. So they specify transformers for each of the steps. It proposes four methods based on this principle. Two of them perform well on our data. So DRG retrieve only retrieves a sentence with the opposite style, which is similar to the original sentence and returns it. And DRG template based takes the style attributes from it and plugs them into the original sentence. Here the performance depends on the methods for the identification of style markers and retrieval of replacements. Words associated with style are typically identified either based on their frequency or some works have used attention weights as features. Alright, so basically what they're saying is in the delete, retrieve, generate method, you delete words, then you retrieve words which can take place, and then you generate or sort of edit the sentence for them to make coherent sense. So the original paper proposed four methods, but they are only focusing on two of them, which perform well on their dataset, on this paper's dataset, which we are reading. So the retrieve only uh, picks up a sentence which is similar to the original sentence but has the opposite style. So they want to minimize the content gap, but since they are picking it from a dataset with an opposite style, so the style would be different. And then template based DRG template based takes the style attributes from it and plugs them into the original sentence. So the sentence which has been retrieved, the styles are picked up from it and then it is placed into the original sentence. So I guess this makes sense. Now you might be wondering how are words associated to style. So they are generally picked up in these ways. So one of them is based on frequency. So if a word occurs much more in sentences which have a particular style, then it sort of makes sense to say that that word is a word which belongs to or has some implication to that style. Also, they use attention weights as features, so they might have seen this word has more weightage to the crux of the sentence. Alternatively, style transfer can use masked language modeling. An MLM trained on a dataset with style labels picks a replacement word based not only on the context but also on a style label. Okay, right. Let me just reread this. An MLM trained on a dataset with style labels picks a replacement word based not only on the context but also on the style label. Alright. An example of such model is mask and infill. It is most similar to conditional BERT method we propose. However, conditional BERT performs additional control over the style and the content preservation and is able to make multi-word replacements. Another similar model of this type is described by Malmi et al. 2020. It has a more complicated structure. There, two MLMs are trained on a corpora of different styles and they perform replacements jointly. Alright, so basically, what they're saying is they're using MLMs, so mass language modeling is basically, if, let's see if I can get some good infographic on this. Masked language modeling. So basically, you mask out some words and then feed it into the language model, and then the model tries to predict that word. So this is one way in which the model learns, and this is also one of the ways in which BERT is trained. Now, since BERT is a mass language model, so they've said that an MLM trained on a dataset with style labels picks replacement words not only based on context but also on the style labels. So obviously, because since it has availability of style labels, then it can also leverage that as a feature. An example of such model is mask and infill, and they say that this was a model which used this method. It is similar to conditional BERT, but they say that conditional BERT differs due to the fact that it gives more control over style, and also it allows for multi-word replacement, which probably the other models do not. So now then they also refer to this paper which used multiple two MLMs. So end-to-end architectures. In contrast to these models, there exist end-to-end architectures for style transfer. They encode the source sentence, then manipulate the resulting hidden representation in order to incorporate a new style and then decode it. Some of them disentangle the hidden representation into the representation of content and style. The others force the encoder to represent style independent content. Alternatively, the model Dual RL by Lu et al. Performs a direct transfer from the source to target style. The task is paired with the dual style back transfer to the source style, which allows model to train without parallel data. So I hope this part is clear. Basically, what they're saying is, in the start of the paragraph, they were referencing to these tasks where you have a sentence, you generate via an encoder a hidden state representation, and then they edit this hidden state representation. Some models so editing to remove the style attributes and add new style attributes. Some models might not do this. Some models, what they would do is use the property that they would try to make sure that this hidden state representation in the first place does not get any style attributes. So this transfer itself should remove the style. And then they talk about this dual RL model, which uh, give me a second, which takes a sentence, then converts into another style, and then converts it back to the same style. So this reconstruction loss sort of setting is there for training without parallel corpus, because you do not have a ground label for this sentence, right? So how would you check if the model is doing well? So you convert it back and check if the model is doing well. Alright, the deep latent sequence model DLSM model by He et al. 2020 use amortized variational inference to jointly train models for the primal and dual tasks. The stable style transformer method trains a pair of sequence to sequence transformer for primal and dual tasks using cross entropy of a pre-trained style classifier as an additional discriminative loss. So I'm not familiar with this work, but this work I've seen. The style transfer as paraphrase strap method by Krishna et al. 2020 views a style transfer model as a paraphraser that adds attributes of a particular style to a text. Alright. The authors create pseudo parallel data by transferring style marked text to neutral with a pre-trained general purpose paraphraser, and then train sequence to sequence model on these neural to styled parallel datasets. Our Parajedi model is conceptually similar to these methods. However, unlike these methods, the style is not infused into the model or a sentence generation, but is imposed on the generator by another model. Alright. So basically, what they're saying in this trap work, uh, the authors created a pseudo parallel dataset by transferring style marked text to neutral. So basically, they had a corpus which had text which was annotated with their styles, and then they use a pre-trained general purpose paraphraser to convert it into to paraphrase it and sort of get the neutral text, and then they were able to train the model sequence to sequence models on these neutral to style parallel datasets. So the output of the paraphraser is used for training. So they say that the para JDI model is similar but uses another model for the style handling. Now detoxification. Detoxification of text is a relatively new style transfer task. The first work on the topic is by Dos Santos et al. 2018 in an end-to-end sequence-to-sequence model trained on a non-parallel corpus with autoencoder loss, style classification loss, and cycle consistency loss. A more recent work by Tran et al. 2020 uses a pipeline of models. A search engine finds non-toxic sentences similar to the given toxic ones. An MLM fills the gaps that were not matched in the found sentences, and the sequence-to-sequence model edits the generated sentences to make it more fluent. Finally, Logier et al. 2021 detoxifies sentences by fine-tuning T5 as a denoising encoder with an additional cycle consistency loss. So I'm not sure what fine-tuning T5 means. Let's look it up. So T5 is a transformer, I guess, but what exactly is T5? T5 transformer. Text to text transfer transformer. Okay, so there are 5 T's, so that became T5, I reckon. Hmm. Yeah, the 5 T's. Let's see. So basically, it's a unified framework for all downstream tasks. Alright, got it. Uh, in these works, they approach a similar problem, preventing a language model from generating toxic text. They do not need to preserve the meaning of the input text. However, the idea of applying a discriminator to control an LM during generation can be used for style transfer, and they've shown it in their experiments. So, prevent, all right. So, I guess this part is pretty clear now. The related works. So now let's have a look at the paraphrasing JEDI model. The recently proposed JEDI model, okay, performs text generation from scratch, guided by a language model informed about specific attributes of a text, like style or topic. We extend this model by enabling it to paraphrase the input text. Sorry. The original JEDI model consists of two components, a generation model GPT-2 and a discriminator model. It is also a GPT-2 trained on sentences with additional sentence style labeling. During training, the style label is prepended to a sentence. Prepended means basically if this is a sentence, then you add the style label here. This makes the discriminating model learn the word distributions conditioned on a particular label. At each generation step, the distribution of the next token predicted by the main model (PLM) is modified using an additional class conditional language model (PD) and the Bayes rule. So the TH token, this basically means the TH token is predicted using all the tokens before it, and C. Here C is the desired attribute, so a particular toxicity or a particular sentiment, and it is proportional to the value predicted by the language model, the token predicted by the language model, based on the sentence words it has predicted before it, and the value predicted by the class conditional language model. So basically, this part is predicting the class. So it's taken all these tokens and it's predicting whether this class is correct for these tokens. The first term is produced by the main language model (PLM), and the second term is calculated using the Bayes rule and additional class conditioning language model (PCC). Thus, the tokens which are more likely to appear in a text of a chosen style get a higher probability. So this part is essentially, this part comes from the Bayes theorem, the Bayes rule, and this part is calculated using a class conditional language model. So it predicts the tokens based on a particular class. The name JEDI stands for Generative Discriminator because a language model which is generative by its nature is used as a discriminator for guiding the generation process. JEDI was successfully applied to guiding a GPT-2 model towards generating text of particular topic and making the generated text less toxic. Now we have para-JEDI. In order to enable JEDI to preserve the meaning of the input text, we replace the regular language model in it with a model capable of paraphrasing. Alright, so the regular language model with a model capable of paraphrasing. Right. So in the original Jedi, they saying that there was a normal language model, but now the model here can also paraphrase. If we denote the original text by X, the generated text of length T by Y, and the generated style by C, para-Jedi models the following probability. So predicting the TH token of the output sentence Y is based on the tokens before it, of course. So this basically means the y less than t or x less than t thing basically means suppose you have predicted the words I am a, and then you need to predict the fourth word, then you can use all the words before it to get additional context since they've already been predicted. And you also have the desired style C. So it is proportional to using a language model to predict the th token using only the tokens before it and the original text, and also to check the class of the predicted tokens, and which can then be approximated. So this probability has been approximated to the probability of using this PD model, which is a class conditional language model whose inputs will only be the tokens and not the original sentence. The last input is an approximation because the class probability should be conditional on both x and y. However, this approximation, although not being fully justified, allows us to decouple the paraphraser model, which requires a parallel corpus for training, from the style model, which requires only text with style label, not necessarily parallel. Alright, so basically what they're saying is if they wanted to do this, then both of them would require parallel corpuses. But since they do not, then this allows them to train both of them separately. The the paraphraser and the style model can be trained independently. Moreover, we can plug in any paraphraser as long as it shares the vocabulary with the class condition language model. uh, we can plug in any paraphraser as long as it shares the vocabulary with the class condition language model. Alright, so it should be familiar with the words which it's going to see. It should not be that every other word is being trained as a unknown token. The third optional component of this model is a re-ranker, an external model which reweighs the hypotheses generated by the style language model guided paraphraser with respect to the style. A re-ranker is a pre-trained toxicity classifier which chooses the least toxic hypothesis generated by the para-Jedi model. So basically, they're saying that suppose the para-Jedi model gives three options, then they can use additionally or optionally a re-ranker model to select which one of them will be the least toxic one. Para-Jedi is trained as follows. Its loss is L loss para-Jedi. It consists of a linear combination of two losses, the generative loss LG used in language model training and the discriminative loss LD, which further pushes different classes away from one another. So you also need to be able to distinguish between the classes to be able to sort of get the correct class label prediction for a particular piece of text. So this is the log likelihood loss for the generative model, and this is the log likelihood loss for the discriminated training model. So these must look very familiar if you've seen other papers, because this is the general form of the losses. And then the net loss is lambda times LD. So lambda times the loss by the discriminator and 1 minus lambda times the loss by the generator. So basically saying that the total loss is a combination of uh, basically if 40% is being contributed by this loss, then 60% by this loss, and so on. We enhance the model with a number of inference heuristics that improve content preservation and increase the style transfer accuracy. First, we use a heuristic from the original JEDI model. We raise the conditional LM probability to the power W greater than 1, which biases the discriminator towards correct class during prediction. Alright. So earlier, since both of them were linear, they had equal weight, but now they've increased the weight for the correct class prediction. Besides that, we suggest two new heuristics. So, smoothing of probabilities. Adding a small alpha greater than 0 to all probabilities discourages the generation of tokens with low probability conditional on all classes. So, if they have a minimum probability, then some token which has a very low probability will not be generated, because this alpha will uh, sort of handle those tokens by having a minimum probability threshold, kind of. So asymmetric lower and upper bound, L and U for class conditional correction. By decreasing the value of U, we discourage the insertion of new tokens as opposed to prohibiting existing tokens. For the problem of detoxification words, than to delete toxic words from the sentence. Sorry, I think I missed a line. By decreasing the value of U, by decreasing this value, we discourage the insertion of new tokens as opposed to prohibiting existing tokens. So since this probability, if you decrease U, then the minimum would then you will have a more higher chance than before to be the minimum. So then this probability of using having the correct class, I guess, would be wrong, but I'm not really getting what they're trying to say here. So, for the problem of detoxification, it means that the model will try less to insert polite words than to delete toxic words. Uh, let's just see again. Okay, so this is the insertion part. So, when you decrease U, you are telling the model to not get new tokens to insert and try to use the existing tokens. So this basically means that the model will not then straight away go and bring very different tokens and change the meaning or style altogether, because then it would not be helpful as a suggestion. Now the conditional BERT model. BERT, Delvin et al. Is the original paper which showcased BERT has been trained on the task of filling in gaps. So a mass language model. We can use it to insert non-toxic words instead of toxic ones. This approach has been suggested by Wu et al. As a method of data augmentation. The authors identify words belonging to the source style, then replace them by masked token, and the BERT model then inserts new words of desired style in the designated places. To push BERT towards the needed style, the authors fine-tune BERT on a style-labeled dataset by replacing segmentation embeddings of original BERT with trainable style embeddings. So the original BERT had these segmentation embeddings, but they've been replaced by style embeddings, which are trained on the dataset which they will use, so that BERT learns to enforce style. We performed some changes to this model to adapt it for the detoxification task. While in the original conditional BERT model, the words are masked randomly. We select the words associated with toxicity. Alright, so it's not like random it or some other word which has less to do with toxicity will be masked. This can be done in different ways. Example, by training a word level toxicity classifier or manually creating a vocabulary of rude and toxic words. So you can just have a lookup dictionary and pick up words which are toxic from there if they occur and mask them. We use a method which does not require any additional data or human effort. We train a logistic bag of words toxicity classifier. This is a logistic regression model which classifies sentences as toxic or neutral and uses their words as features. As a byproduct of the training process, each feature yields a weight which roughly corresponds to its importance for classification. So basically, if it's a toxicity classifier and there's a word which is contributing heavily to it being toxic, then that word is likely to be a source of the toxicity. The words with the highest weights are usually toxic. We use the normalized weights from the classifier as a toxicity score. So the overview of conditional word is as follows. There's this sentence, and firstly they detect the toxic words, then they create multiple possible substitutes, and then they re-rank the substitute by similarity and toxicity. So they do not want a word which totally changes the meaning, making it making it non-hateful at all, because then the model will be useless, right? Because you cannot suggest it to someone who wants to post something toxic. For each word in a sentence, we compute the toxicity score and then define toxic words as the words with the score above a threshold. Okay, where these are the scores of all words and T-min is minimized. Okay, so they pick up the highest toxicity and divide it by 2, and they also have a minimum threshold. So if this goes below that, then they won't then this T-min will be chosen as maximum. This adaptive threshold allows balancing the percent of toxic words in a sentence so that we avoid cases when too many or no words are marked as toxic. To preserve the meaning of the replaced word, we employ the content preservation heuristic suggestion. So they preserve the original tokens instead of masking them before the replacement, and re-rank the replacement words suggested by Bird by the similarity of their embeddings from the embedding of the original word. Okay, so I think I did not get this paragraph, so I read this again. To preserve the meaning of the replaced word, we employ the content preservation heuristic suggested by. Okay, so the words which are coming, they need to have uh, meaning or sense in the sentence. So they preserve the original tokens instead of masking them before their replacement. So they keep the tokens which were supposed to be there. They re-rank the replacement word suggested by Bird by the similarity to the embedding of the original word. Alright. So suppose there were three words predicted, then they'll get vector representations of all of these words, and then they'll measure the similarity with the word which they want to replace. So this would so they might be using some sort of distance metric, say a cosine metric, and they'll see that which word is most close to it. So if some word is totally an antonym, then it would be very far away. Despite using class-specific sentence embeddings, conditional BERT often predicts toxic words, apparently paying more attention to the context than to the embeddings of the desired class. To force the model to generate non-toxic words, we calculate the toxicity of each token in BERT vocabulary and penalize the predicted probabilities of tokens with positive toxicities. So what they were saying that when they use this model, the one which they've described so far in that form, then they noticed that BERT was predicting toxic words. So it was giving more importance to content than to the style part. So they to do that they penalized it if it gave very toxic words as outputs. Finally, we enable BERT to replace a single mask token with multiple tokens. So like here, the word hate is replaced with the word disagree with. We generate each next token progressively by beam search and score each multi-token sequence by the harmonic mean of the probabilities of its tokens. So you can see that now they've also finished describing the conditional BERT model. So now I'll just pause for a minute and I'll be back after having some water. So I'm back, so I'll just remove this. Okay, so the detoxification experiments. We trained the two new models and a number of other systems for text detoxification below. Below we describe datasets, evaluation setup, and results. So for the toxicity classifier, we trained two binary classifiers of toxicity. One of them is used to re-rank hypotheses in the para-JEDI model, and the other participates in the evaluation. So this part, which is ranking the toxicity, uh, where did it go? Yeah, and the other participates in the evaluation. We train these two classifiers on different sets of data. The overall dataset is a merge of English parts of the three datasets by Jigsaw, containing around 2 million examples. We split it into two parts and fine-tune a Roberta model on it. We use the Roberta large model from the original repository. The classifiers perform closely on the test set of the first Jigsaw competition, reaching the area under curve ROC of 0.98 and F1 score of 0.76. Alright. So they'll be using this for testing and also the ranking part. The dataset for training and testing of the style transfer models, we use the English dataset from the first Jigsaw competition. The majority of our methods are trained on non-parallel corpora of source and target style. To prepare the toxic dataset, we divide the comments labeled as toxic into sentences. To prepare the toxic dataset, we divide the comments labeled as toxic into sentences. Like, acha, okay. So basically, if the comments are too long, they break them down into sentences and classify each of them with a toxicity classifier. Sentences classified as toxic are used as toxic part of dataset. So they had 154,000 of them. To select the neutral part, we randomly pick the small number of non-toxic sentences. The test set is prepared analogously to the test set of the Jigsaw competition. We used 10,000 sentences with the highest toxicity score according to our classifier. The test set is prepared. Alright, so for toxic sentences, they pick the top 10,000 of these. I'll just alright, so the metric, there is no parallel test set available, so they cannot use Blue, Meteor, or Rogue metrics and resort to referenceless evaluation. Style transfer models need to change the style, preserve content, and produce a fluent text. These parameters are often inversely correlated, so we need a compound metric to find a balance between them. They follow the evaluation strategy of Krishna et al. And use the metric J, which is a multiplication of sentence level style accuracy, content preservation, and fluency. The system level J is the average of sentence level scores. Style accuracy ACC is measured with pre-trained toxicity classifier. So this one which they mentioned here, which will be used in evaluation. Content preservation SIM is evaluated as a similarity of sentence level embeddings of the original and transformed sentence. So basically, how similar are the sentence before and after going through the model. Fluency is measured with the classifier of linguistic acceptability trained on the COLA dataset. So how fluent the generated text is. J is computed as average of their sentence level product. In addition to that, we tried a similar aggregated metric GM, which uses perplexity as the measure of fluency and employs a different aggregation method. Our preliminary experiments show that J and GM are strongly correlated, so we keep only J for further evaluation. So since GM and J will show the similar results. Implementation detail. For ParaJedi, we use a pre-trained T5 model, text to text uh, transfer transformer, and a base paraphraser fine-tuned on random subsample of the para and empty dataset. As a discriminator, we fine-tuned the GPT-2 medium model on the training part of the Jigsaw 1 dataset using two color codes for toxic and polite texts. Before fine-tuning, we changed the vocabulary of the discriminator to match that of T5 and update its embeddings accordingly. We trained the discriminator using a combined generative and discriminative loss, adapting their code for this purpose. Alright. So basically, they have a GPT-2 medium model which will act as a discriminator. The discriminator essentially needs to classify, and it was trained on the Jigsaw 1 dataset using the two toxic and polite parts. Then they fine tune it, and before fine tuning it, uh, fine tuning the GPT-2 medium model, uh, so it has already been trained. So they update the vocabulary so that both the models have similar vocabulary. I'm really sorry about the disturbances. So I'm really sorry about the disturbances, but I live with my parents and there's a lot of disturbance due to random relatives popping up all the time. We trained a discriminator using a combined generative and discriminative loss from Krause et al. 2020, adapting their code. Alright. We use beam search, decoding with 10 beams to generate paraphrase candidates with the paraphraser and discriminator described above. We applied a classifier from section 5.1 to select the least toxic candidate from the 10 resulting paraphrases. So I guess this part is now clear. They are referencing to these classifiers, re-ranking one. So the competing methods, we compare our model with state-of-the-art methods described in section 2, DRG template-based DRG retrieve-only mask full DLSM, strap and SST. We also implement three other baselines, machine translation, detoxifying GPT-2 and paraphraser. We do not directly compare our models with JEDI because it is a language model and was not explicitly trained to transform texts. So now machine translation, there is evidence that automatic translation tends to eliminate toxicity. Thus, we use a chain of a machine translation model for detoxification. So English is some pivot to English translation. We chose French and Igbo as pivot languages. French is resource-rich and structurally similar to English, which ensures high-quality translation. Conversely, Igbo is low resource and syntactically different. Both experiments are conducted using Google Translate API. Detoxifying GPT-2. GPT-2 can be adapted to a wide range of NLP tasks using a very small task-specific dataset. We experiment with the model's ability to perform sequence-to-sequence tasks. We train it on a parallel dataset of 200 toxic and safe sentences. We randomly select toxic sentences from the Google Jigsaw toxic comment dataset and manually rewrite them in the neutral tone. So they've annotated it themselves and fine-tuned. They've trained the GPT-2 model on it. For the paraphraser, they use Krishna et al. 2020 suggestions that a general purpose paraphraser can remove style markers from the text, and then they check this assumption. So let's have a look at the results. The performance of all tested models is given in table 1. Both para-JEDI and conditional bot outperforms other models by a large margin. The success of conditional bot is explained by its use of heuristics targeted at the companies or components of the metric. So the success of conditional bot is explained by its use of heuristics targeted at the components of the matrix. So if you remember, we had a look at them earlier. It is penalizing for generating toxic tokens, which ensures a high accuracy score. So if you remember, uh, it was told to not generate toxic tokens, which the problem which we discussed earlier. Over 80% tokens stay unchanged because we were rewarding it for lower distance between original and final sentence, and the replacements are selected with respect to the similarity to the original words, increasing the overall SIM score. So if just want to check, SIM is the content preservation evaluation score, and MLM is pre-trained to replace mask tokens with plausible substitutes, including fluency. ParaJedi is behind in terms of similarity but has similar, slightly higher fluency because generation is a better strategy for natural text because GPT-2 is, of course, a text generation model. The closest competitor is Mask and Infill, which uses similar principle of conditional word. However, some engineering decisions, example masking of all words at once, results in a substantial drop in fluency and some decrease in style transfer accuracy. Surprisingly, many advanced models perform below the simplistic DRG model, template-based and retrieve-only. Template-based achieve a high similarity because it keeps most of the original sentences intact, and retrieve-only yields a high similarity and style transfer accuracy because it outputs real non-toxic sentences from the training data. So these are previous models which we are looking at. So template based gives high similarity because it uses the template of the original sentence, and retrieve only yields high similarity and style transfer because it outputs real non-toxic sentences from the training data. So it's retrieving essentially. DLSM and SST models perform full regeneration as opposed to pointwise correction. More importantly, their decoders are trained from scratch on a relatively small dataset, hence their low fluency. Conversely, Strap, which also generates the sentences, has access to a larger pseudo-parallel data, resulting in higher fluency. Another finding is that MT has detoxification ability, machine translation. However, it is inversely correlated with its quality. So, English to Igbo to English detoxifies 37% of sentences, but has low so SIM was uh, the con- the style content preservation. Sorry, was So it has low content preservation and fluency. Conversely, when you use French, it yields better output, which keeps most of the original features, including toxicity. The same applies to a T5 paraphraser. On the other hand, GPT-2 model can be trained to detoxify even on very small a number of parallel sentences, so they only use 200 sentences. Although it performs below many other models, which suggests that training on large parallel dataset can boost its performance. Additional examples can be found. Okay, so now the parameter selection. Our models use multiple parameters and heuristics. We perform an evaluation study to explore the usefulness. It turns out that crucial features of conditional bot are multi-word replacement, which ensures high fluency and toxic penalty, which increased style strength. On the other hand, masking of all tokens at once as well as control of similarity do not affect the quality. More details of the conditional bot evaluation study are given in Appendix B. Alright. ParaJedi has only one training hyperparameter lambda, which controls the strength of its discriminative loss. We discover, so if you forgotten, this lambda was the one which I was saying that it tells how much each loss is going to contribute. Um, Here, so the higher the lambda, the more contribution of the discriminative loss. The value of j decreases only for lambda 1, which constitutes the absence of generative loss. The style strength control influences the style accuracy, whereas the use of word probability upper bound increases similarity, and the absence of beam search decreases fluency. So all of these are the different things which I mentioned earlier. On the other hand, re-ranking, beam size, smoothing do not affect the model performance. An ablation study is also in Appendix C. Mining a parallel detoxifying corpus. So the strap model is based on the assumption that a regular paraphraser can transform a stylistically marked text into neutral text. Although our experiments show that paraphraser as well as an empty model are bad detoxifiers on their own, we suggest that it is possible to find occasional detoxifying sentence pairs in a large parallel dataset of paraphrases. So not always, but sometimes it can. Experimental setup to test this hypothesis, we classify the sentences from the para and empty dataset with our toxicity classifier and obtain 500,000 paraphrase pairs where one sentence is more toxic than the other. We then compare the regular paraphraser from section 5.4 fine-tune on the random set of para and empty with its version fine-tune on mind toxic safe corpus. We also plug both paraphrase into para-JDI model and compare the overall performance. Alright, so you can have a look at the law strength of lambda and compare it to the loss. So how much greater lambda corresponds to strong influence on discriminative loss and smaller lambda means stronger generative loss influence. And comparisons, so these are the scores for different parameters. So let's have a look at, so the input is no room for those stupid antics, and paraphrase one does there's no space for all these adversities, conditional but no room for those bizarre exploits. All right, so their score is significantly higher as far as I can see. This should be lower or not, I'm not sure. Fluency should be high, of course, and j also. The asterisk denote the scores are significantly higher than the third best model with probability less than, okay, p less than 0.01 based on the pair t test. So green just means that these are the models which Dave suggested. Gray are the baselines. Didn't mean to do that, but we can see that the model is performing pretty well, even beating the humans at times. All right, so did I miss some part? We were here, right? So the human part comes later. So the experimental setup to test, yeah, so we've read this. Discussion of results. None of the paraphrasers can fully detoxify the test set, but the mind paraphraser gets a better ACC than the regular one. When we replace the regular paraphraser with a detoxifying one, both detoxification rate and fluency improve without the loss in similarity. This leaves us with a J score of 0.54, which is the highest score we obtained. We do not include it in the main result because the model is not unsupervised. However, this result shows that general purpose para and empty corpus contains a large number of toxic to safe paraphrase pairs. We believe that mining parallel training sets from large corpora as opposed to unsupervised methods is a fruitful direction. Alright. So human evaluation. While the automatic reference-free evaluation is cheap and fast, it may be unreliable. Toxicity and fluency classifiers are not perfect. True, true, true. The embedding distance, which is used to measure the content preservation, was shown to weakly correlate with human judgment. So then they use humans. We design a manual evaluation setup to be as close as possible to automatic setup. We evaluate our models on the same metrics. For all metrics, they have a ternary scale 0, half, or 1, corresponding to a bad, partially acceptable, and fully acceptable sentence. We ask 5 annotators to evaluate the models. Annotators are NLP researchers with MSc degree or above and with good command of English. Prior to the annotation, we arranged a preliminary round to reach common annotation understanding. Each sentence is evaluated by 3 annotators. The final score for a sentence is computed by average. We measure the entire annotator agreement. We obtain the score of 0.42 for style, 0.31 for content, 0.52 for fluency, a moderate agreement for style and fluency annotations, and a low agreement for content annotation. We evaluate 3 models: Parajedi, Condbert, and Mask and Fill, whose automatic scores were the highest. The evaluation was conducted on 200 sentences by each of the evaluated model. The input sentence for the evaluation was manually pre-selected to filter out disfluent or senseless utterances. So they were not pre-selecting on the basis of output but on the basis of input. To compensate for the low inter-annotator agreement, we annotate each sample 3 times and report the average score. Discussion of the result. We show the performance of models here in the table 4. So you can see that according to manual evaluations, the Parajedi is scoring highest in all of the metrics. The model scores the average sentence scores. We combine the 3 metrics into a joint metric. Sentence level JM is multiple, right? So we've discussed this before. This manual evaluation corroborates the superiority of the model over mask and infer. At the same time, it confirms that the 2 models are not significantly different. Although Parajedi outperforms conditional BERT, the difference in score is statistically significant only for the fluency. Otherwise, it's not statistically significant. Beside the evaluation itself is investigated to what extent the automatic metrics reflect the human judgment. To do that, we compute their Spearman's P correlation with human judgment. For style, we consider the accuracy of toxicity classifier and we use uh, that we use for evaluation its version which returns the confidence instead of a binary label. For content, we use SIM, right, and blue score between the original and detoxified sentence. For fluency, we consider the linguistic acceptability classifier and perplexity of the GPT-2. This evaluation shows that tested metrics of content preservation show only weak correlation with manual scores which agree to the previous research. The correlation of automatic style and fluency metrics with human judgment is moderate. It turns out that the confidence style classifier is a better style accuracy metric than a binary classifier, and the acceptability classifier works better than perplexity, confirming the criticism of perplexity as a fluency metric. So, I guess this part was pretty self-explanatory. They talked about how they were using different metrics to describe the metrics, how they there was uh, like the annotators did not have very high agreement, so they had to annotate every sentence thrice, and based on that, then they checked used different classifiers for testing, and they report about how other works have also reported about some metrics not being a good metric for certain tasks, such as style transfer. So again, these are the scores. Sentiment transfer experiment. Text detoxification is not a well-established task, which makes it difficult, right? So experimental setup, we train Parajeda and conditional bot on the Yelp dataset and compare them with mask and infill SST and so on. We tune the hyperparameters. We evaluate a model using J and so on. Then they compute the scores. Parajeda outperforms other models in terms of J as before the other models fail to generate fluent text. because they replace only specific words or because they learn to generate text from scratch. Parasite model is the only comparator which combines uh, pre-trained models and full regeneration. The performance of the conditional BERT model is low on this task, corroborating that detoxification and style transfer for other domains require different techniques. Right. So, on the other hand, the blue score questions this result. Compared to the human references, the best performing model is dual RL followed by 2 MLM, masculine infill, and conditional BERT. The evaluation of reference human answers also questions the referenceless metrics. First, we see that ACC score is limited by the classifier performance since it gives only 0.81 to presumably 100% correct manually written sentences. The small difference in ACC could not be considered significant, and the ACC above 0.81 is unreliable. However, since the score of human answers is close to that of Parajedi and Masker Infant, Parajedi can still be considered a strong style transfer model, and more precise evaluation should be done by human because metrics cannot distinguish between models at this level. So basically, what they're saying is most metrics agree that Parajedi is outperformed every other model, but the blue score metric does not give it a higher score. Then they go on to justify why. The conclusion: we present two style transfer models tailored for detoxification, that is transfer from toxic to non-toxic text. Both of them combine high-quality pre-trained LMs with extra style guidance. Parachita is based on a paraphraser guided by a style conditional GPT model. GPT-2 model. Convert model is based on BERT, which does not need any fine-tuning, and all style control is performed with a pre-trained toxicity classifier. We conduct a large-scale study of style transfer models, exploiting both automatic and manual evaluation. Our experiments show that proposed methods outperform other state-of-the-art style transfer models on the task of detoxification. Then they have their ethical statement of what is toxicity, toxification of text, and detoxification as a censorship. So you might want to go through these, but I won't because the video is already getting quite long. I reckon how long has it's already more than 1 hour, and still there is a lot of thing left. They've also thanked the laboratory which helped them uh, do the experiments. Let's have a look at the appendix. So they've defined their text detoxification task. Then they have the ablation studies. You can see that the full model is better in, but when you only use mask all tokens, you get this. When you have no similarity penalty, the accuracy goes down and so on. They have a similar one for para Jedi, which you can have a look at. They also have a qualitative analysis. Alright, so they've shown experiments, but I won't be reading through them because they have some really toxic words in them. So if you want, you can go through this paper yourself. So thank you guys for joining in. As always, do like, share, and subscribe, and comment down below any suggestion which you might have. This was a great paper to read, and I personally really enjoyed because the way of writing was pretty good for this paper and probably one of the better style transfer papers which I've read.